Hello, and today is about the element zinc. So most zinc is used to galvanize other metals such as iron to prevent rusting. Galvanized steel is used for street lamps, safety barriers, and suspension bridges. Large quantities of zinc are used to produce die castings, which are important in the automobile, electrical, and hardware industries. Zinc is also used in alloys such as brass. Here's some information on brass. Zinc is also used in alloys such as brass, nickel silver, and aluminum solder. Zinc oxide is widely used in the manufacture of many products such as paints, rubber, and cosmetics, textiles, ink, soap, batteries, and electrical equipment. Zinc sulfide is used in making luminous paints, fluorescent lights, and X-ray screens. The major uses of zinc metal are in galvanizing iron and steel against corrosion and in making brasses and alloys for die casting. Zinc itself forms an impervious coating of its oxide on exposure to the atmosphere, and hence the metal is more resistant to ordinary atmospheres than iron and corrodes at a much lower rate. In addition, because zinc tends to oxidize in preference to iron, some protection is afforded to the steel surface even if some of it is exposed through cracks. The zinc coating is formed either by hot dip galvanizing or electrogalvanizing, seen here. As previously mentioned, it is used in paints, cosmetics, plastics, pharmaceuticals, and printing inks. Because under the influence of light, the electrical conductivity of zinc oxide can be increased many times. It is employed in certain photocopying processes. Zinc sulfate, ZnSO4, is an intermediate compound in the production of zinc from its ores by the electrolytic process. It is used as a weed killer in the manufacture of viscose, rayon, and in dyeing, in which it functions as a mordant. A mordant or dye fixative is a substance used to set dyes on fabrics by forming a coordination complex with the dye, which then attaches to the fabric. It may be used for dyeing fabrics or for intensifying stains in cells or tissue preparations, according to Wikipedia. Zinc chloride, or ZnCl2, can be prepared by a direct reaction or by evaporating the aqueous solution formed in various reactions. It is strongly deliquescent, water absorbing, and is utilized as a drying agent and as a flux. In aqueous solution, it is used as a wood preservative. Zinc sulfide or sapphirite, ZnS, has luminescent properties when activated by the addition of small quantities of copper, manganese, silver, or arsenic, and so has been used in X-ray screens, in luminous dials for clocks, and watches and fluorescent lights. Zinc is an essential trace element in the human body, where it is found in high concentrations in red blood cells as an essential part of the enzyme carbonic anhydrase, which promotes many reactions relating to carbon dioxide metabolism. The zinc present in the pancreas may aid in the storage of insulin. Zinc is a component of some enzymes that digest protein in the gastrointestinal tract. Zinc deficiency in nut-bearing and fruit trees causes such deficiencies as pecan rosé, little leaf, and mottle leaf. Zinc functions in the snail's blood to transport oxygen in a way analogous to iron in the hemoglobin of human blood. Zinc oxide is used as a semiconductor in the production of phosphors for television tubes and fluorescent lamps. Its effect on the reactivity of many compounds make it useful as a catalyst in such operations as a manufacture of synthetic rubber and methanol. So metallic zinc appeared much later in history than other common metals. Copper, lead, tin, and iron can be obtained as the molten metal by heating their oxides with charcoal or carbon, a process called reduction in shaft furnaces, which were developed quite early in history. Zinc oxide, however, cannot be reduced by carbon until temperatures reached well above the relatively low boiling point of the metal, or 907 degrees Celsius. Thus, the furnaces developed to smelt the other metals could not produce zinc. Small quantities of metallic zinc can sometimes be found in flues or blast furnaces. There is some evidence that the Greeks knew of the existence of zinc and called it pseudo de gras, or false silver, but they had no method of producing it in quantity. The Romans as early as 200 BCE produced considerable quantities of brass, or CuPbZn, which consists of copper, lead, and zinc, an alloy of zinc and copper, again, by heating in crucibles a mixture of zinc oxide, or ZnO, and charcoal, covered with lumps of metallic copper. The zinc oxide was reduced in the lower part of the crucible. Zinc vapor was formed and dissolved in the copper to form brass. At the end of the process, the temperature was raised to melt the brass, or CuPbZn, for cast into ingots. Brass production was the Romans' only use of zinc. The realization that to make zinc it was necessary to produce the metal as a vapor and then condense it seems first to have been reached in India in the 13th or 14th century. The metallurgists in China had achieved large-scale production of zinc by the 16th century. In the West, this principle was first applied in England in 1743 under the leadership of William Champion. William Champion is credited with patenting a process in Great Britain to distill zinc metal from calamine using charcoal in a smelter, according to Wikipedia. He was born 1709 and he died 1789 in Bristol, United Kingdom. So at the end of the 18th century in Belgium and Poland, improvements were made in the furnace and the process remained unchanged until an electrolytic process was developed in 1917. At the end of the 1920s, a radical advance was made in the United States by developing a continuous retort process, and in the 1930s an electrothermic process was designed for producing zinc continuously. A development of the 1960s was the zinc-lead blast furnace, in which rapid quenching of the gases is a key principle. Zinc production processes are treated in detail in zinc processing. So metallic zinc is produced by roasting the sulfide ores and then either leaching the oxidized product in sulfuric acid, H2SO4, or melting it in a blast furnace. Zinc is won from the leach solution by electrolysis, where it is condensed from the blast furnace gas and then distilled of impurities. Zinc is found in several ores, the principal ones being zinc blende, zinc sulfide, ZnS, and calamine, zinc silicate. The principal mining areas are in China, Australia, and Peru. Commercially, zinc is obtained from its ores by concentrating and roasting the ore and then reducing it to zinc by heating with carbon or by electrolysis. World production is more than 11 million tons a year. Here we have calamine. It's a historic name for an ore of zinc, zinc carbonate, or ZnCO3, or smithsonite. Zinc silicate, Zn4Si2O7OH2, and water, or hemimorphite. Zinc is essential for all living things, forming the active site in over 20 metalloenzymes. The average human body contains about 2.5 grams and takes in about 15 milligrams per day. Some foods have above average levels of zinc, including herring, beef, lamb, sunflower seeds, and cheese. Zinc could be carcinogenic in excess. If freshly formed zinc 2 oxide is inhaled, a disorder called oxide shakes or zinc chills can occur. Again, a review, zinc, Zn chemical element, a low melting metal of group 12 of the periodic table that is essential to life and is one of the widely used metals. Zinc is of considerable commercial importance. So a little bit more abundant than copper, zinc makes up an average of 65 grams or 2.3 ounces of every ton of Earth's crust. The chief zinc mineral is the sulfide safflerite, or zinc blende, which together with its oxidation products, smithsonite and hemimorphite, constitute nearly all of the world's zinc ore. Native zinc has been reported from Australia, New Zealand, and the United States, and the leading 21st century producers of zinc are China, Australia, and Peru. Freshly cast zinc has a bluish-silver surface, but slowly oxidizes in air to form a grayish protective oxide film. Highly purified zinc, 99.99%, is ductile. The so-called prime western grade, 99.8% pure, is brittle when cold, but above 100 degrees Celsius or 212 degrees Fahrenheit can be rolled into sheets that remain flexible. Zinc crystallizes in the hexagonal close-packed structure. When iron, Fe, and zinc, Sn, together are exposed to a corrosive medium, they constitute an electrolytic cell, and the zinc is attacked, oxidized to the Zn2 ion, preferentially because of its higher electrode potential. This so-called sacrificial protection, coupled with the much greater corrosion resistance of zinc under atmospheric conditions, is the basis for galvanizing. Natural zinc is a mixture of 5 stable isotopes. The only difference between these isotopes is the number of neutrons that they contain. Other than that, they have the same number of protons. Here to protect and serve. I'm more useful than you'd ever zinc. I'm a very sociable element that's always happy to mix in with other metals. Brass is probably my most well-known alloy, formed when I get together with copper. On my own, I can be found in batteries. With a thin layer of my atoms, I quote-unquote galvanize steel, stopping water and oxygen from rusting it away. Even if I am scratched and the steel gets exposed, I quickly form zinc oxide before iron in the steel has a chance to corrode. I also protect people from sunburn as the white zinc oxide sunblock that can be seen on the noses of lifeguards. What's more, I'm an essential element for lots of body processes, and I can be taken as a dietary supplement. Its date of discovery was 1500. Its density is 7.140 grams per centimeters cubed. Its melting point is 419.53 degrees Celsius or 787.15 degrees Fahrenheit. Its boiling point is 907 degrees Celsius or 1665 degrees Fahrenheit. Here's zinc and a metal being dipped into it. Although this element was not recognized until the 18th century, compounds of zinc have been in use for many centuries. Calamine lotion, for example, contains zinc oxide and is an ancient recipe for soothing itches. Its atomic mass is 65.38. Its state is solid. Its discovery was in 1746 by Andreas McGrath. Here's a laboratory sample of pure zinc. So that was zinc explained in 18 minutes or less. If you like this video, make sure to like, comment, and subscribe. Other than that, thank you everyone for watching. Have a great one.